Hey, welcome everyone. Today we're going to be doing superdense coding. That's a quantum communications protocol, and it's going to essentially allow us to send two classical bits of information with just one qubit of information. That's why it's called superdense. Sorry, stage left. That's why it's called superdense information coding, because it shows that qubits have way more information density than classical bits have. So let's see how that works. We've got Alice here, and we got Bob on the other end of a classical channel. And Alice is going to send just one qubit, and Bob is going to receive two classical bits of information, right? One, two. So that's why it's called superdense. Let's see how this works. We talked about these last time, these kind of Bell states, but the first step is going to be to make a Bell state, or an EPR state, as I called them last time from the Spooky Information at a Distance paper by these three guys. The first step is to actually run a Hadamard gate over a regular kind of qubit in a classical state of definitely 0 or definitely 1. If you run it over a definitely 0 state, you get this out, normalization factor plus 0 plus 1, right? So this is the square root. The Hadamard gate is sometimes called the square root of flip, or the square root of not, rather, because it doesn't quite flip a bit. It puts it actually kind of halfway in between flipped and not flipped in this linear superposition of maybe 0, maybe 1. In fact, this normalization factor gets squared, and this is actually sort of a coin flip. This is actually sort of like a fair coin before you check it, but the quantum version. So there's a half probability of it being 0 and a half probability of it being 1. Now you take this and use it as the control bit in a C not gate. This is what we did last time. And you put a regular bit through, let's say in the 0 state, and the first part of the 0 bit comes out. Oh, we better index these or we're going to lose track. This is two separate qubits. So we're going to call the control the A, and we're going to call this guy the B qubit. This is Alice's qubit, and this is Bob's qubit, okay? And the notation I'm actually going to be using and have been using kind of looks like this. This is actually shorthand for this. Two separate qubits, each sitting in their own little Hilbert space. This is shorthand for this, and that in turn is shorthand for this. They're each in their own Hilbert space. This is a tensor product. It's a Cartesian product between Hilbert spaces, and they can each have their own vectors slash wave function slash wave states. Eigenstates, right? This is what these guys are. Now back to this. These are Alice's, and this is Alice's qubit, and this is Bob's qubit. So we're using this as a control qubit. So Bob's qubit is the one that's actually being operated on. The control qubit doesn't really get touched by this operation. So first, Alice's just kind of goes through. Bob's goes through the NOT gate, but Alice's, it's the first component of this linear superposition, says, I'm a 0. I tell the NOT gate to not do its job because I'm a 0. So Bob's doesn't get flipped, right? Oh, sorry, let's undo that. Bob's doesn't get flipped, right? Cool. That makes sense. Now, Alice's goes through the control bit, as the control bit will do, and then the control bit says, I'm a 1, do your job, NOT gate. And then the 0 does get flipped. So now we have 0, 0, 1, 1. This is a Bell state. It's our first Bell state. There are 4 of them total. You'll see that, what was it, 2 classical bits of information. 2 to the 2 is 4. In general, 2 classical bits of information can encode 2 to the n, an alphabet with 2 to the n symbols. So in the English alphabet, there's 26 characters. So if I wanted to encode, um, if I wanted a little slot of memory and I wanted to be able to store any character in the English alphabet on that like little slot of memory, how many bits of memory would I need for that? The answer is 26, but they come in twos, so 2 to the 5 is 32. So I would need 5 bits of memory in order to store any arbitrary symbol in the English language. There are 4 Bell states, so I need 2 qubits, and that's what we're able to transmit here. Back to the Bell states. So Yeah, this is a Bell state, properly normalized, of course. Square root of 2. Cool. So we got our Bell state. What do we do with it? And by the way, the Bell state is Alice and Bob's qubit. This is two qubits, a linear superposition of two qubits entangled. Notice here that if Alice and Bob were in different galaxies, the Andromeda and the Milky Way, if Alice measured her bit, her qubit, and it came out as 0, Bob all the way in the Andromeda could never really talk to her, but Alice would know that Bob's bit was actually in the 0 state. Seems weird, right? That seems a little bit strange. And that's spooky. That's the spookiness Einstein was talking about. So that's what entanglement really means. And in fact, the Bell states are the maximum amount of entanglement. Whoops. The maximum amount of entanglement that two qubits can have. That's why they're special. That and they're used in a lot of these kind of quantum algorithms and things like this. Like this one. Let's go back to it. So now that we have our Bell state, we're going to actually separate these two. Um, and Alice is going to take her quantum circuit and she's going to decide which message she wants to send to Bob. She can send one of four different messages. She can send a 0, 0, she can send a 0, 1, she can send a 1, 0, or she can send a 1, 1, right? Our alphabet of four different symbols here. And let's say she has like a quantum computer or quantum circuit here. And there's these four buttons here that she can press now to operate on her qubit. So if she presses 0, 0, it goes to the identity gate. If she presses 0, 1, I believe it goes to the X poly gate, I want to say. Let me double check myself on that. Ignore that. 0, 1, yes, that's correct. 0, Z, Z gate, I, and then I times the Y poly gate if she wants to go through 1, 1. So good, she's operated on her qubit now. And now what happens is over this classical transmission line, just a normal transmission communications line, right? Like any other way we'd use. She sends her bit to Bob. Now Bob has both qubits, right? So again, the transmission used only one qubit, Alice's qubit. Bob's qubit was not transmitted. Bob just has it. He had it in his pocket. He walked away, right? So now the transmission only used one qubit. When with that one qubit, we're going to transmit two bits of information. How are we going to do that? Well, Bob is sitting here and he only received one qubit from Alice, but now he has both qubits. So how's he going to know what Alice transmitted to him? Well, he's going to perform an operation, specifically this one. The Hadamard gate tensor product with the identity operator. So this is his kind of like quantum computer here, his little quantum circuit, and it's going to operate on the qubits that he has. So we don't really know what theoretically what Alice sent, but let's just say she sent um, 0, 0, 1, 0, 0. What is it? Um, uh, 1, 1, 0, 1. That's what she sent. There we are. Okay. So no, not that one. 0, 1, 1, 1, 0, 1, 1, 1, 0, 1, 1, 1, 0, 1. Right, that was it. 1, 1, 1, 0, 1. Yes. Okay. Good. Very good. Okay. Standard algorithm. 1, 1, 0, 1. Okay. Now we're going to perform this operation on it. And what does the Hadamard gate do? Oh, this needs some clarification probably. This again is shorthand for this. Hadamard gate only operates on Alice's bit. And again, remember, I should really be indexing these. This is Alice's bit, this is Bob's bit, so he has both now. Yeah, let's Wikipedia open in case I forgot any of this. It's been quite a while again. 0 bit. Okay, so Bob has both bits now, so he's going to perform this operation on them to try to figure out what Alice is trying to tell him through this wire. Now, Hadamard gate acts on 1, and the 1 bit going through the Hadamard gate is going to give us 0, 1 plus suitably normalized. Proud I only had to check Wikipedia once. Okay. And then Bob's qubit, it's the identity gate on it, plus 0 plus, oh, this is a 1 bit, minus plus 1 suitably normalized. Okay. And then the 1 bit again, very nice. Okay, so this 0, 1, 0, 1, and again, A, B, right, minus 1, 1, plus, plus 0, 1, plus 1, 1, away, away, and you see only the 0, 1 survives. Hooray! We successfully transmitted a 0, 1 over a classical communication channel with only 1 qubit. Wonderful. Okay. So this is how we can superdense code things, and this is one of our first quantum circuits that we're going to see. A little bit simple. Next time we're going to do quantum teleportation. It's a little more exciting. We're going to do something a bit similar to this, except we're going to be transmitting a quantum bit, a quantum state. Now, one more thing that I neglected to mention up until now, which is actually extremely important, and now that we're talking about quantum teleportation and the sending of a quantum state seemingly in violation of locality, but we'll talk about that. I should really mention something called the no cloning theory, and I'm going to give a proof of this next time, but I have to mention this now. You cannot replicate a quantum state. Um, there's nothing wrong with doing this in classical physics. If you have a physical state, you can make a copy of it. You cannot absolutely not do that in quantum mechanics. You can't do it. So if I have a quantum state, I can't take it and just make a copy of it. That's absolutely not acceptable. I can prepare identical quantum systems, but I can't take a quantum state, look at it, and make a copy of it. That's not okay. I can take a quantum state and make a copy in a way that destroys the original. That's totally fine. But I cannot absolutely not, in a quantum computer, replicate a quantum state and leave the original unscathed. So there's another classical circuit that's absolutely not allowed because of this. It's called fan out. Now, in classical computers, there's a circuit that takes a classical bit and makes a copy. That's not allowed in quantum computation. It's absolutely not permitted. So I just thought I should mention that before we proceed, and especially before we go to quantum teleportation, which absolutely destroys the original quantum state. You can't copy them. Okay, very nice. So cheers, everyone, and I'll see you in the next lecture.